Hello everyone, welcome to Neso Academy. We are learning theory of computation, and in the previous lecture, we have understood the 5 basic building blocks of TOC: symbols, alphabets, strings, languages and grammars. And now you are all set to understand automata and its types. I hope you all remember the automata theory that we have discussed under the topic Pillars of TOC. There, I have told you that to solve a computational problem, we design an abstract machine or an automata. And now in this lecture, we are going to understand automata in detail. So let's see all the topics of this lecture. Our first topic is automata or an automaton, in which I will explain you what is an automaton in theory of computation. And our second and last topic of this lecture is types of automata, in which I will explain you about the 4 different types of automata. So without any further delay, let's start with our very first topic, that is automata. Automata is a mathematical model of any machine that processes an input string by moving through a sequence of states according to defined transition rules. So, as we already know by the automata theory, that an automata is a mathematical model or a diagrammatic representation of any machine to solve a computational problem, and it processes an input string. So we have an input string and our automata will process that input string. But how will it process the entire input string? We already know that our string is made up of the finite sequence of symbols, and the automata cannot process the entire input string at once. So our automata will read only one symbol at a time in order to process the entire string. And how will it process? By moving through a sequence of states. That means this string will be processed by our automata by moving through a sequence of states, like state number 1, then state number 2, then state number 3, and so on. And this processing will be in according to defined transition rules. Now, what are transition rules? Transition means the process of moving from one state to another state. That means if we are moving from state number 1 to state number 2, then we call it a transition from state number 1 to state number 2. And the set of rules that define these movements are called as transition rules. So transition rule tells us that which state will come next on the basis of the current state and the current input. Now, it is not always necessary that there is a transition from state number 1 to state number 2. There can also be the transition from state number 1 to directly state number 3. But that depends on the transition rules and the current input symbol. Now, suppose we are on the state number 1 and input symbol is X. Then there is a transition from state number 1 to state number 2. But if the input symbol is Y, then there is the transition from state number 1 to state number 3. So in this way, we can conclude that transition rules tells us that which will be the next state on the basis of current state and current input symbol. And now I hope that you all have understood what is an automata. It is a mathematical model of any machine that processes an input string by moving through a sequence of states according to defined transition rules. Now, if I ask you, when will the processing of this input string stops? Processing of this input string will stop once all the symbols of this input string will get processed. And when all the symbols of this input string will get processed, there will be 2 possibilities. Either our automata will accept this input string or it may reject this input string. So if the automata accepts the input string, it means that the processing of this input string stops at a state called as accepting state. And If the automata rejects the input string, it means that the processing of this input string stops at a state other than the accepting state. So it means that if the computation or the processing of the input string reaches the accepting state, it accepts the input, otherwise reject it. So, while processing this input string, if the processing stops at the accepting state or the final state, it means that our input string is accepted by the automaton. And if the processing of the input string stops at any other state other than the accepting state, let's say state number 4, then our input string is said to be rejected by the automaton. So now I hope that you all have understood what is an automata and how does it work. Now to concretize what we have just studied, let us take our same example of login system. So here is a login system of a website. First of all, user will enter his user ID. Then the user will enter his password. If the password is correct, user will get the access to his account. But if the password is a wrong password, the login system will again ask user to enter the password. Now, we are required to construct an automata for this login system. So let's design an automata or an abstract machine for this login system. So this is the very first state of the login system or our automata. This is called as an initial state because this is the first state of an automata. And in automata, initial states are represented using an inward arrow and a circle. This state is enter ID. That means the login system is in the state in which it is requesting the user to enter his ID. When the user enters the ID, there will be a transition from state number 1 to state number 2, which is enter password. Now, the login system is in the state in which it is requesting the user to enter his password. Now, there are two possibilities. If the user enters the correct password, he will get the access to his account. But if the user enters the wrong password, he will again be asked to enter the password by the login system. Let's see. If the user enters the wrong password, he will remain at the same state, that is enter password. And when the user will enter the wrong password again, he will again remain in the same state. But when user enters the correct password, he will reach the state number 3, that is access granted. Here, user will get the access to his account. Now this state is called as the final state or the accepting state of an automata. And in automata, final or accepting state is represented using the double circles. And why this is called an accepting state? Because this is the state where correct passwords are accepted. Now I hope you all understand how to construct an automata. And in this way, we have completed with our very first topic, that is automata. Now let's proceed with our second topic, types of automata. So in total, there are 4 different types of automata. First one is finite automata, in short represented as FA. The second one is push-down automata, that is PDA. Third one is linear bound automata, that is LBA. And fourth one is Turing machine, that is TM. So these are the 4 types of automata that we will study in detail in our upcoming lectures. And now we are going to discuss the properties of these automata. So some properties of these automata increases as we move from top to bottom, that is finite automata to Turing machine, while some other properties will decrease as we move from finite automata to Turing machine, that is from top to bottom. So first of all, let's discuss the properties which increases on moving from top to bottom. So the first property is memory capability. Memory capability increases as we move from top to bottom. That means finite automata has a very limited or small amount of memory, while Turing machine has infinite amount of memory. The second property is problem solving capability. It means that finite automata can solve a very limited variety of problems. And Turing machines can solve even almost every problem that is solvable by our computers. The third property is computational power. So it is very obvious that finite automata has the least computational power, while Turing machine is the most powerful model of computation. So these were the properties that increases when we move from top to bottom, that is finite automata to Turing machines. Now let's discuss the properties that will decrease as we move from top to bottom. The first property is restrictions. That means finite automata is the most restricted model of computation. There are many rules and regulations to follow, while Turing machine is the most unrestricted model of computation. The second property is simplicity. So finite automata is the simplest model of computation. Finite automata is easier to construct as well as to understand, while Turing machine is the most complex model of computation. It is complex to construct as well as to understand. So these were the properties that decreases when we move from top to bottom. And in this way, we have discussed all the properties of these automata which increases or decreases as we move from top to bottom. And in this way, we have completed our second topic, that is types of automata. So this was all from my side for this lecture. Thank you, and I'll see you in the next lecture.